It's glamorous, colorful, exciting. It's RCA Victor's new Mark Series Color TV, with a picture so bright, so true, you have to see it to believe it.
What you just heard was a commercial for color TV in the 1960s describing the revolutionary power that color brought to television back then. Here at the Interplanetary Exploration Institute, we're bringing color to methane detection. Hi, I'm Jay Bevington, the founder of the Interplanetary Exploration Institute, and we're really excited to share with you what we've been working on. Methane is a potent greenhouse gas with about 25 times more warming power than the carbon dioxide that we so often hear about. About 40% of human emissions come from the energy sector, and another 40% comes from agriculture. But these two industries are not making the same progress on reducing their emissions. In the energy sector, many countries have implemented regulations to help curb emissions. Though viewed skeptically, companies are making progress. Satellite data has proven particularly valuable in detecting leaks. Motivated by profits, companies are keen to keep product in the pipeline rather than lost to the atmosphere. Until recently, methane emissions were quantified through conversion factors. For example, a leak rate per kilometer of pipeline was just assumed rather than actually measured. Satellites making these actual measurements showed about 60% more emissions. This would have been a big surprise, but also represented unrealized costs to these energy companies who now have methods and market incentives to do what is best for the environment. In comparison, the agriculture sector is not regulated. Recent proposals in the New Zealand and European Union have been met with fierce protests and are unlikely to move forward. In many cases, farmers have blocked major roads and even driven tractors and livestock into capital cities, creating chaos. Unlike the energy sector, actual measurements of emissions in agriculture are just lacking. And as a result, there are few market incentives to reduce emissions. For example, in the UN and Australian inventory framework for cattle, the primary conversion factor is based on livestock weight. Thus, for a farm to reduce emissions often means reducing profits too. That's not a very incentivizing prospect. It's no wonder then that only 3 cattle projects in Australia have generated carbon reduction credits since the system's establishment in 2015. To break the impasse, we need measurement capability that gives farmers not only market incentives to act, but also more methods than just weight reductions to do so. To understand how to measure agricultural emissions, we first need to understand why it's so hard. In the energy sector, emissions are often point sources, like pipeline leaks or oil well off-gassing. These point emissions are large and concentrated, making them quite easy to spot. But also, the emission source is easily identified by the location of the point source itself. An emission over a pipeline is, well, most likely from the pipeline. In agriculture, emissions arise from millions of animals and thousands of farms spread across large areas. Located between these farms are other emission sources too that can confuse things. Emissions over a regional area could be from, well, anything. As a result, ascribing a source type to this geographically distributed methane is difficult at best and in many cases impossible. The Interplanetary Exploration Institute and its partner, Macquarie University, have developed a new sensor to fingerprint methane by its source type. We aim to map this fingerprint globally by flying our sensor on satellites and imaging the Earth. The fingerprint is based on methane molecules with extra neutrons that are specific to the source that created the methane. We can see these features by breaking sunlight into millions of colors, in much the same way your eyes can distinguish the colors of the rainbow. The sensor works by converting light into radio frequency electronic signals. Once in radio, we can use decades of signal processing technology to measure the fingerprint and ascribe a source type to the methane, regardless of its location. So far, our team has made substantial progress towards realizing our goal. Through simulation, we have demonstrated the fingerprinting method is capable of determining source type, even when other leading satellites could not. Further, we've constructed a benchtop prototype and used it to successfully fingerprint methane in the lab. We strongly support the future of agriculture, the environment, and the planet, and we look forward to empowering the future that we know is possible.